Hi, g'day, Dr. Carl here with Dr. Graham Wild
Correct.
from ADFA, which stands for
The Australian Defence Force Academy.
to talk about the new improved weapon that will change everything called the hypersonic plane. And yet, didn't we have hypersonic stuff in World War II with the V2?
Yes, that's correct.
Okay, so we're talking aircraft. We're talking moving really fast. So you're going to educate me about hypersonics and us. How did you get into this?
I guess my father was the most influential person on me with regards to this. So when I was a young boy, we used to stay up late watching Discovery Wings. So I used to learn about things like the F-111, the F-15, F-16, F-18s and the F-14. And that became something that I became really obsessed with, was fast-moving aeroplanes. And I remember going back to England on a holiday when I was young, seeing fighter jets fly over. I mean, it was lovely seeing the Hawks and the PC-9s at the time flying around in Australia, but it's not the same as seeing tornadoes and other things fly over in England. And luckily, people on the East Coast here could see F-111s and F-18s and things like that. But growing up in WA wasn't really a thing. So, but seeing that and the Concorde and other things became very enamoured. So when I found out that this was a possible career path and I was moving into physics and going to go to the University of New South Wales to do aerospace engineering, I got an opportunity to do research with the CSIRO into what I do now, structural health monitoring for aerospace vehicles, and that's the path I chose to take, was that applied science and engineering of...
So what degrees did you get along the way?
So I've got a science degree from Edith Cowan University in physics and mathematics.
Physics and mathematics is a good start, yep. And then?
I've got a master's degree from the University of New South Wales in photonics and optoelectronics.
Photonics, that's dealing with light for various information.
So I put optical fibres in hypersonic vehicles as my primary area of research.
Ah, okay. And then after the master's degree?
I've got a PhD in engineering.
What sort of engineering? Aerospace?
Well, I mean, technically I'm a physicist, but it's the optical fibre sensing for structural health monitoring of ageless aerospace vehicles.
Okay, so now please tell me whenever I say something wrong, because you're the expert and I'm not, so you know about this aviation stuff. What they're saying is that if you're flying aircraft in a war zone, you've got two main choices. One is stealth and the other one is speed.
Yep.
And so there's this big push for hypersonic, and that's why we're talking hypersonic today, which is like 5,000 kilometres an hour, whole new ballpark. Oh my God, where should we start? We'll start with subsonic.
Yeah, so let's get some definitions that you feel we need.
Okay, so with an aeroplane with a little fan on the front,
Yep.
you can get up to about, 500 kilometres an hour or something?
850.
Really?
Yep.
What about a propeller?
Propeller? Yeah, 500 would be a good speed.
So you've got a propeller and it's pulling the air through.
Yep.
And then you have this thing called the jet engine. And what it does is it squirts kerosene.
Yep.
Oh, by the way, we're defining the speed of sound to be 1,000 kilometres an hour. It's close enough. It varies, And we're trying to talk about Mach 2, that's 2,000 kilometres an hour, Mach 3, 4, 5, 6, okay? With a jet engine, how does that work?
So the common engine you see on most aeroplanes these days is the turbofan, and a turbofan is not much different to a turboprop. And so it's hard to tell when you say a propeller-driven aircraft. Most people will think that it's got a piston engine like a car. But most propeller-driven aircraft that people will see these days, unless they're small things like Cessnas and Beechcraft and things like that you might see at some small metropolitan airports. If you're still at a large airport and it has a propeller, it's still got a jet engine that's turning that propeller.
And there are certain fuel advantages and all that sort of stuff.
Thermodynamic advantages. So the actual efficiency of those engines is about twice the thermal efficiency of a piston engine.
Okay, so your little tiny aeroplane like a Cessna is just an internal combustion engine.
Like a car.
That turns a propeller. And then at the airport, you'll see a turboprop,
an ATR, like an ATR 72.
Or a Dash 8.
Yeah,
and so they've got a propeller, but the propeller's not driven by a piston engine, it's driven by a jet engine.
Correct.
Why do they do that? And
again, so it's about twice the thermal efficiency for a gas turbine compared to a piston engine. So you're already doubling the fuel efficiency. It's also surprisingly more reliable and less maintenance for a jet engine.
Because you don't have stuff that goes backwards, forwards.
Things aren't rubbing as much. Yep.
So it just goes in the same direction. So you've got to... How does a jet engine work? My understanding is that you squirt kerosene and light it.
Yep.
I'm sure there's more to it than that.
So the simple mechanics of it that everyone talks about is the suck, squeeze, bang, blow concept, and that works for pistons.
Suck, squeeze, bang,
blow.
Oh my God. There should be a band with that name.
Yeah,
Okay, lay it on me.
So obviously the inlet, so the air going in, and again the aeroplane is going at 850 kilometers per hour. The air's got to go into the engine. That's the suck part, and then that slows down quite a lot.
So the air gets sucked in by a fan or some sort?
No. So it's just the inlet. So it's like having the opposite of a water jet. So a jet or a nozzle is designed to collimate the water together or the fluid together and push it out faster.
Yeah.
And you do a diffuser is the opposite shape to that, and that allows the fluid to expand and slow down.
Right.
So it's just the opposite of what a nozzle's doing. So that's what the inlet of a jet engine is. Like think about a Boeing or an Airbus.
So it's a suck?
Yeah, so that's the suck
Even
part.
though it's not actually sucking,
Yeah.
it's just pushing through the air. So suck, then squeeze.
The squeeze is what the compressor's doing. So effectively just like your pump in a fish tank or something like that. So we pump liquids and we compress gases. So
and it's got little blades on it.
yeah, that's right.
And by the way, we are heading for this SR-71. We are heading for something that'll fly hypersonic, but so we're just working our way up. So I heard once, tell me if I'm wrong again, that a blade that does the squeezing inside a jet engine can generate, just that little blade the size of the palm of your hand, can generate like as much power as a big V8 petrol engine, like 500 horsepower or something?
Yeah. So
is that true?
Yeah, of course. So you've got to remember
just a little blade.
when our coal or gas plants have an issue and they can't use their primary burner, they will have a 50 megawatt gas turbine that burns kerosene as their emergency backup. So when a large power plant stops working, there's Siemens and Rolls-Royce build these large jet engines that are just there to turn a generator.
Are they bigger than the jet engines on aeroplanes?
Oh, yes.
Oh, okay. Right, because I remember going on an Antarctic explorer ship, and they had various backups, and the backup to the backup to the backup, because they would be an icebreaker, and they go in so far that they could not be rescued.
Yep.
Nobody could rescue them. If they were stuck, anybody would also be stuck.
Yep.
And so they had these enormous jet engines that,
that's
on
right.
the other hand, would always work, but on the other hand, burn fuel like there was no tomorrow.
Oh, yeah, that's right.
Okay, right. So we got the suck, we got the squeeze, we got the blades, and so you compress the air, and then suck, squeeze, bang. Okay,
so
tell me about the bang.
that's when we inject the kerosene.
Really?
And then we ignite the kerosene. So again, just like most things. So think about a barbecue. So you've got the propane that you're burning with a flame. Same thing happens. So that we've got a spark igniter that generates a flame, and then that flame front stays, and then more fuel and air goes past that, burns more, and then that starts the expansion.
Oh, wow. I hadn't thought of that concept. So you've got a flame front. So if you were able to look in the engine, you'd see this burning stuff, and then molecules of air
And fuel. Yep.
and molecules of kerosene would come in, and they would combust, and the flame front would stay where it is, but the atoms would come in and go out the other side.
Correct.
And the blow bit?
And so that's the important thing that we were mentioning before that people weren't privy to, is that air is coming in at only about 1 kilometre per hour. So it's very slow, and that's why it's not being blown out.
Hang on, wait a sec. You got the speed of sound is 1,000.
Yep.
The airplane's doing 850.
Yep.
If it's a normal single aisle or double aisle passenger jet. And so it's doing 850 kilometres an hour through the air. The front of the engine is doing 850 kilometres an hour. The air coming into the front of the engine is doing 850. And you're telling me that in the combustion zone, it's going at 1? That's slower than a walking pace.
Yeah, that's right. And that's why the flame doesn't get blown out. It doesn't get blown away. It's able to just sit there, and the engine is designed to keep that flame there.
It's hurting my head, but I feel we should keep on going. And then when it comes out the back, it's doing how fast?
Depending on the exact engine, it'll be doing greater than the speed of sound.
What? So on a normal single aisle 737 Airbus, it's going.
So it depends on the engine. So, but if you've got a pure turbojet, then you've got supersonic flow coming out.
The air's going faster than the speed
So
of sound.
if we're talking about old school F111, FA18, where you can get shock diamonds and things like that.
Oh, but we're not, but not your passenger jets.
So passenger jets, we usually have a requirement that the air pressure on the outside is the same everywhere. So you come back out at 1 atmosphere. So you're going to come out with a lot more speed than you go in, but it will be greater in total than it is without. So you'll still have an airspeed. Again, everything I do is in meters per second. So if you've got an aircraft that's doing 300 meters per second, the air will probably be coming out about 500 meters per second.
So it's coming in the front at 300, but coming out at 500, or say coming in at 800 and coming out at just under the speed of sound.
Yep.
Okay, so that's your normal jet engine.
Boeing Airbus, yep.
And so that'll get you, say, up to the speed of sound, a bit under the speed of sound. Okay, then, so can you, with that sort of engine, and you don't care about the noise, can you then go supersonic, which means the speed of sound?
Yeah, so the F-35 and the new generation FA-18s, and even the older generations, they have what we call a low bypass ratio turbofan.
Low bypass ratio turbofan.
So that's just how
Wow.
big the thing is relative to the size of the engine. So a propeller has a bypass ratio of about 50 to 1. So that means for every litre of air that goes through the middle of the engine, 50 litres goes through the propeller.
What? So for every litre of air that goes into the engine and is burned, so we're talking a Dash 8 or
Yep.
a ATR 72, for every litre of air that goes into the engine and is burned
Yep.
in a jet engine,
The propeller is moving about 50 litres.
oh, so that provides the forward push.
That's
through
right.
the
Yeah,
air.
yeah. So that's the concept of propulsive efficiency.
So they're getting most of their propulsion not from the air being pushed out of the back,
No.
but from spinning that propeller
Correct.
at the front.
100%.
Okay, so is that a low or high bypass?
That's an extremely high bypass ratio.
So that's with a jet engine running a propeller plane.
Yeah.
Now what about a pure jet?
So for a modern Boeing or Airbus, they're about 11 to 1. So for every litre that goes through the engine, 11 go through the fan.
Oh, so the engine has an internal part and a part where air goes through that isn't getting compressed?
Correct.
Really?
Yeah.
And so what's that ratio, 11 to
About
1?
11 to 1 is a very high bypass ratio.
Okay,
these
let's not
days.
dive into that. So how fast can you go then with this turbo jet engine?
So the F-35, for example, does Mach 1.6, and that's very easy to do with a low bypass ratio turbofan.
And I've heard about a thing called an afterburner. What
Yep.
the heck is that?
So with an afterburner, what you do is you have some unburnt air, especially since a lot of air in an engine is being used not for burning, it's used for cooling. So you've got this burning that's going on at 2,500 degrees.
Wow, 2.5. So you've got to have exceptional materials.
Or air films, literally thin sheets of air that stop the flame touching the metal. So you
Right.
have these sheets of air that prevent the flame from touching the metal. So you have all this cooling air that you're using. So a lot of the air that comes out of the engine hasn't been mixed with fuel and hasn't been burnt. So there's still a lot of oxygen in it. So what you do in the tailpipe is you just dump in more fuel and you light it again.
Now, I met somebody, now tell me if this is wrong, they were saying that the F-111, which apparently could fly at Mach 3.2 for about 5 minutes before it began to soften
Bubble and warp.
and change shape, because it wasn't made of titanium, like my favourite plane, the SR-71. Do you know, I've been in the front seat of an SR-71
The lucky man?
twice.
Really?
Does that make you a little bit jealous?
Oh, I've only touched one at the museum.
You actually touched one. Oh, aren't they like works of? They're beautiful. I exhort anybody, if they ever get a chance to get near an SR-71, it's a beautiful thing. By the way, I wasn't flying.
Yeah.
Okay, I was only on the ground. Okay, I have to tell the truth. And so the SR-72 is the next one. We're heading towards that. So the SR-71 could fly at Mach 3.3
Yep.
indefinitely. But with the F-111, it couldn't. It was only about 5 minutes, 5 minutes or so before it began to bend. And they told me that if you were just flying regularly in F-111, you could fly for 7 hours. If you had the afterburner, 20 minutes. Does that sound reasonable?
Yeah.
What, 7 hours to 20 minutes? You're burning up fuel at 20 times the normal rate?
Yeah.
Really?
Yeah.
20 times?
So I go through this with my students. So I teach Defence Force training officers how aeroplanes work. And when I show them the fuel consumption for a Boeing or an Airbus, it's about 1.7 litres per second is the fuel consumption rate. And that is, and you have to think about how much, think about your car. If it burnt 1.7 litres of fuel per second, you wouldn't be getting very far.
But you're moving a couple of hundred people,
Yeah.
150 people.
Yeah, sure.
And you're moving them at high speed, and you can cover a distance that would take you 5 weeks to walk in
Yeah.
1.5 hours. So that's not a bad.
Oh no,
payoff.
it's a great trade-off in terms of the time taken and how fast you get to go and how far you can go. But yeah, so when you go to an afterburner and you've got to push even harder, because you've got to remember that drag goes with the square of velocity. So if you double your velocity, 4 times as much drag, and that's the force of resistance. So you've got to push 4 times as hard to go twice as fast. So we're talking about the F-111 going 3 times as fast. So it's got to push 9 times as hard. So a 20-fold increase in fuel consumption wouldn't be impossible with other losses and efficiencies and things like that.
Okay, so we've gone from the propeller run by a petrol engine to the propeller run by a jet engine, and then the pure jet engine, which in an F-111, you just had to squirt fuel in like crazy and you go fast. The SR-71 had a better system. So it went from, turbojet to... Can you explain what a ramjet is?
Sure.
And by the way, with this guy here, we're going to be heading for the scramjet. Okay.
So the thing we didn't mention with that the engine is that suck part, because we said it's a bit.
So what's the 4 words again?
The suck, squeeze, bang, blow.
I love that paradox.
So that suck part, it
Yeah.
goes from 850 kilometers per hour, and it's going to slow down to 400 kilometers per hour. That's just from that diffuser. And so if it's slowed down, what we can do is we can use Bernoulli's equation. We technically shouldn't apply it there because we're probably going a bit too fast. But we can use Bernoulli's equation, and that's relating the conservation of energy in the flow.
Yep.
And here we've got an exchange between how fast our flow is going and what the pressure is.
So you're balancing one. So the total energy in the airstream is the same. So if one energy goes down, the kinetic energy, the other energy, the pressure energy goes
Correct.
up. So the total energy is the same. So what sort of engine are we talking about?
This is for your Boeing and your Airbus, a Rolls-Royce GE engine.
Before we get into the Ram jet.
Yeah, so what that diffuser's done is it's halved the speed and it's doubled the pressure at the beginning of the engine for free.
Yeah.
So we've done nothing except slow the air down, and by slowing the air down, we've compressed the air.
Okay, so that's the squeeze bit.
And so in the SR-71, in a ramjet, that is all that engine is doing. It's just basically a very complex diffuser that's slowing the air down from Mach 3.5 to 1 kilometer per hour in the engine, so you can then inject fuel and burn it. And that going from Mach 3, so going from 3,000 kilometers per hour to 1 kilometer per hour in an efficient way, means that you have significantly increased the pressure, so you now have pressurized fluid that you can then squirt fuel in and burn.
And
for free.
And it's normally kerosene still?
Yeah, that's right.
But it's sort of professional kerosene,
Yep.
and there's two grades for lower temperatures,
Yep.
jet fuel A, jet fuel B.
Yep.
Basically, it's kerosene. So does that mean that when the SR-71 was doing at Mach 3.2 and it could do it for hours, and what protected it, I believe it had been shot at something like 1,000 times. Was one ever brought down? Maybe one, maybe not.
I don't believe one was brought down by a missile.
No, on one occasion they went too fast and the nose fell off or
Yep.
something, which does kind of happen.
Yeah.
So were the blades having to spin in a compressor? Were the blades having to spin?
Not when it's going Mach 3.5, so 3.3. So it completely bypasses the engine core.
Bypass the engine. So because somehow you've managed using the engine in its regular mode. So the SR-71 engine. Love you, SR-71. You're so beautiful. So the engine switched from regular turbojet to a ramjet. Can you just tell me again? You're not lying about this 1 kilometre per hour. So
it's
even
really,
in a ramjet.
So it's really simple. Lighter.
Yeah.
Drive down the road. Stick your hand out the window. See what happens to the flame.
It has to travel at 1 kilometre an hour, even though the aircraft is travelling at 3,000 kilometres an hour. Okay, so the SR-71 was flying for a while, and then there's been a whole bunch of things. So now we should sort of talk politics and hypersonic, because with trying to shoot an incoming aeroplane. Now this is just part one of the conversation with Dr. Graham Wild. It turns out that this is just such a huge, enormous topic that we've had to split the vodcast into 2 parts. So tune in next week when we dive into part 2, and where I finally begin to understand what the word hypersonic actually means, as well as getting closer to understanding the science behind sonic booms. Shirtloads of Science is washed, spun and aired by the University of Sydney.